Good evening. I am Dr. G. Seshadri, working as Associate Professor in Institute of Aeronautical Engineering. Today I want to discuss about the rotating magnetic field in alternators, induction motors. So AC machines, induction motors and synchronous, both synchronous and asynchronous alternators. So synchronous motors also. So in these AC machines, we are discussing about rotating magnetic field, production of rotating magnetic field in three-phase induction motor. So whenever a three-phase supply is given to the alternator induction motor winding, so or when a three-phase winding is energized from a three-phase supply, a rotating magnetic field is produced. So it is asynchronous motor and it is singly fed induction motor, and this field is such that its poles do not remain in a fixed position on the stator but go on shifting their positions around the stator. So it has induction motor has both stator and rotor, and it is the flux is the field is here. The magnetic fields are three types: pulsating magnetic field, rotating magnetic field, and constant magnetic field. So the magnitude of this rotating field is constant, and it is equal to the 1.5 times maximum the flux. So because it is having three phases, so let us say the three phases X, Y and Z, or maybe R, Y, B. The three phases are denoted as R, Y, B, red, yellow and blue. So the currents are induced in these three phases. Whenever a three-phase supply is given to the winding, induction motor winding, a rotating magnetic field is produced at constant flux phi m of 1.5 times phi m, and the rotating magnetic field rotates at speed is synchronous speed. So the speed is equal to 120 by P, and the fluxes produced in the three phases. So let us say the flux produced in X phase or R phase equal to phi m sin omega t. If we are taking X phase as reference here and assuming the field is rotating in anti-clockwise direction, the rotating magnetic field is produced, and assume that here the rotating magnetic field is in anti-clockwise direction. And if we are taking the X phase as a reference phasor, Y phase is displaced by 120 degrees. So the 360 degrees is divided for three phases: X phase, Y phase and Z phase. So it is separated by displaced by 120 degrees electrically displaced. And to the X phase, Y phase is 240 degrees, separated by 240 degrees. From Y phase, it is 120 degrees to the Z phase, and if we are considering from X phase, it is nothing but 240 degrees. From X phase, Y is displaced by 120 degrees. From X phase, Z is displaced by 240 degrees. Okay. So we can see the equation for flux in the consecutive phases are phi x, phi y and phi b. Phi x equal to phi m sin omega t and phi y equal to phi m sin omega t minus 120, that is which is lagging by 120 degrees to the x phase, and phi z equal to phi m sin omega t minus 240. And how the flux is produced in the rotating magnetic field. So here the flux is nothing but here 3 fluxes will be produced here, and if the flux produced in R phase equal to like this, and the 3 phases R, Y, B, exactly it is starts, Y phase starts after 120 degrees and B phase starts after 240 degrees. So here the maximum flux at any instant, the maximum flux can be determined. So here phi m is the maximum flux in any phase, and here the 3-phase supply is causing the production of rotating magnetic field at constant magnitude, which is equal to phi resultant flux equal to phi m into 1.5 or 1.5 times of phi maximum. So at any instant the current in phase x is 0 and currents in phase y and z are equal to opposite. So the currents are flowing outwards in the top of the conductors and inward in the bottom of the conductors. Here we will see the derivation for a resultant flux here. So here the resultant flux establishes towards right, and the magnitude of resultant flux is constant and which is equal to 1.5 maximum, 1 times of maximum, and is rotating at a synchronous speed. So at any instant, let us take omega t or theta equal to omega t, angular velocity, the theta equal to 0 degrees, and therefore under the 3 fluxes, therefore the 3 fluxes phi x. So here, since here the theta equal to 0, sin theta, that means phi m sin theta, phi r or phi x equal to phi m sin theta. So here we are applying theta equal to 0 degrees, so phi x, the flux in the x phase equal to 0. Similarly, if you apply the same theta equal to 0 in y phase, in equation 2, the phi y equal to phi m sin omega t minus 120. So here, if you apply here phi y, phi m into sin of minus 0 minus 120, sin minus 120, which is equal to sin of minus 120 is nothing but minus root 3 by 2 into phi m. Similarly, phi z equal to, substitute this theta value 0 here by substituting sin 0 minus 120 minus 240, which is nothing but sin is minus 240, sin of minus 240 equal to plus root 3 by 2 plus root 3 by 2 into maximum value. And the phasor sum of both phi y and phi z will give the value of resultant. So total resultant value phi r equal to negative value. So if the phi r is, phi x is 0, so it is not considering here, and phi y equal to, phi y value, phi y equal to minus root 3 by 2 phi m, it is phi y, and phi z equal to here plus root 3 by 2 of phi m. So Since it is negative of phi y, we can draw this vector minus root 3 by 2 here instead of drawing in original. We can draw oppositely for considering minus root 3 by 2 phi m. So the resultant of these two will gives the phi r. So phi r equal to here 2 into root 3 by 2 phi m cos 60 by 2, that is 2 into root 3 by 2 root 3 by 2, which is nothing but 3 by 4, 2 root 3 by 4, 2 root 3 into root 3, 3, 2 into 3 by 4, which is nothing but 3 by 2, which is nothing but 1.5. Here, at any instant, the current is maximum in this, at this instant, the current in, that is current in x phase equal to 0 and the current in y phase equal to minus root 3 by 2, flux in z phase equal to plus root 3 by 2. So the magnitude of resultant flux equal to 1.5 times of 1.5 times. So we are taking at any instant 2, the theta value equal to 0, theta equal to 30 degrees. Similarly, we'll get the fluxes in x, y, b phases, x, y, z phases. In one phase, the value will be 0, and other phase, the value will be minus root 3 by 2, and another phase, the value will be plus root 3 by 2. So, resultant again 1.5 times of maximum flux. And if we consider the theta value 60 or 90 or 120, 180, 270, 360, the same values 1.5 times of phi max will be the final resultant value. Then the phasor sum of phi y and phi z is the resultant flux. And similarly, in other cases also, other instances also, just the resultant flux is displaced clockwise from position 1. From position 1 to 2, the flux will be displaced 30 degrees actually. Here we can observe the resultant flux in different cases. So this is case 1, case 2, case 3 and case 4. Waveforms also for x phase, for y phase and for z phase. Waveforms. Fluxes will be produced here, and at instant 1, 2, 3, 4 we can derive at any instant the value will be 1.5 times of maximum. And next instant also the same value. The current in phase z is 0 and the currents in phase x and y are equal and opposite. So the currents in phases x and y are 0.866 into maximum value. So this magnitude of resultant flux is again 1.5 times. So the vectors for different rotations, different instances we can observe here. So here we are considering flux value, we are considering theta value is 0. In x it is, the value will be 0. The flux in x will be 0. And in y it is minus root 3 by 2 and z it is plus root 3 by 2. So resultant again, this value is resultant. So the difference between, the phase difference between phi x and phi r is 30, and similarly the difference between phi x and minus phi y is again 30. But it is equally displaced from each phase. The displacement is 120, 120, 120. And second case, we are taking next theta equal to some other angle. It is at a second instant it will be 30 degrees or 90 degrees. and different instances we can draw the resultant value. We can observe that the resultant vector is rotating for each and every instant. So at each and every instant it is rotating and to 30 degrees. Here also 30. After this 30 it is rotating, and here it is rotating after 30 degrees. So let us say if theta equal to omega t, in another case theta equal to 60, the same values will be, in one phase it will be 0 and another phase it will be equal and opposite. Another two phases it will be equal and opposite. So minus root 3 by 2 and plus root 3 by 2. So the resultant flux everywhere it will be equal to same 1.5 times at any instant. The resultant flux is displaced 60 degrees from position 1. From position instant 1 to 2 it is 30, and from position 1 to next position it will be displaced by 90 degrees, 60 degrees. Same, similarly procedure is same for instant after considering theta equal to omega t equal to 90 degrees also. So phi x equal to, since it is sin 90, it is value is 1, so maximum value will be phi m. And it, in case of phi y it will be minus phi m by 2, and in phi z it will be plus phi m by 2. So the phasor sum of minus phi z and minus phi y equal to same 1.5 times of minus phi m. So the resultant flux is downward, that is it is displayed as 90 degrees clockwise from position 1. So it follows from the above discussion that three-phase supply produces a rotating magnetic field at a constant of 1.5 times of phi m. So where phi m is the maximum flux due to any phase. And speed. At what speed the rotating magnetic field is rotating. The speed at which the rotating magnetic field resolves is called as synchronous speed. So synchronous speed is denoted as ns, capital N suffix s. So it is again, we know the synchronous speed equal to 120 into f by p, where f is the frequency, supply frequency, and p is the number of poles. So at instant 4 means it represents the completion of 1 quarter cycle. So if it is the 1 cycle, at instant 4, 1, 2, 3, 4. It is 1 quarter cycle. It is time period is t, and at quarter cycle the time period is 1 by 4t. So the time instant 4 represents the completion of 1 quarter cycle of alternating current Ix from the time instant 1. During this 1 quarter cycle, the field has rotated through 90 degrees. At a time instant represented, or one complete cycle of current Ix from the origin, the field has completed 1 revolution. Therefore, for a 2-pole stator winding, the field makes 1 revolution in 1 cycle of current. In a 4-pole stator winding, it is 2 cycles, 1 revolution in 2 cycles of current. In general, for p-poles, the rotating magnetic field makes 1 revolution in p by 2 cycles. So 1 revolution completes in p by 2 cycles of current. So speed. So cycles of current is nothing but number of revolutions of field into p by 2. So cycles of current per second is equal to revolutions of field per second into p by 2. So since the revolutions per second is equal to revolutions per minute is divided by 60, ns equal to seconds, revolutions in seconds equal to revolutions in minute equal to revolutions in minute equal to, so for 1 minute 60 seconds, so since 1 minute equal to 60 seconds, so revolutions per second is equal to the revolutions per minute divided by 60, will gives the number of cycles per second, which is nothing but number of cycles per second equal to frequency, which is nothing but hertz. So frequency equal to number of cycles per second into p by 2. So number of cycles per second into p by 2, and number of cycles per second is nothing but number of cycles per minute by 60, which is nothing but nsp by 120. Finally, ns equal to 120 f by p. So speed of rotating magnetic field is the same as speed of alternator that is applying power to the motor. If the two have the same number of poles, the magnetic flux is said to rotate in synchronous speed. And direction of rotating magnetic field. The phase sequence of three-phase voltage applied to the stator winding is XYZ or RYB. If this sequence is changed to RBY or XZY, it is observed that the direction of rotation of field is also reversed. If the sequence is reversed, the direction of rotation of field is also reversed. So the field rotates in counterclockwise direction rather than clockwise. The field rotates in rather than clockwise direction, it rotates in counterclockwise direction. So however, the number of poles and the speed at which the magnetic field rotates remains unchanged. So it is necessary only to change the phase sequence in order to change the direction of rotation of magnetic field. So for a three-phase supply, this can be done by interchanging any two of the three lines. So the rotor in a three-phase induction motor runs in the same direction as the rotating magnetic field. So this is all about the rotating magnetic field. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.